Alright, hello everyone. This is week 5, I think, so lab 4, and let's get to it. So this week we're going to learn how to determine the transient and steady state responses for second order systems that have different inputs, like a step input, an impulse input, and a ramp input. We'll talk about what those are. Step and impulse should be familiar to you from vibrations. So here's the general form for a second order system as a transfer function, and I'm going to derive it for you because you should know how to do it. So a second order system is simply a mass spring damper system, and that equation of motion can be represented here. We start with sum of forces equals ma, so here's ma, here's the spring force, here's the damped force, and here's our input forcing. Right, there's always an input. We're going to take the Laplace, transform. We're going to put all the x of s's on one side. We're going to factor out the x of s. And now we're going to organize this so that way we have our output, or what we're interested in, on the top, and our input on the bottom. So we're inputting our force, and we want to see how the system, how its displacement responds to our input. So this describes our system. This is the system's output. What we're interested in is its displacement, and our input is r of s. Okay, so dividing by m, we get this, and then we also want to multiply by k over k. Before I get into why we multiply over k over k, we're going to make sure that we know that k over m is wn squared. We can reorganize this so that way we get 2 zeta wns, and then let's talk about k over k. So by dividing by m, we get 1 over m. Then I multiply by k over k, so that way this becomes k over m, which we already know is wn squared. So we're left with 1 over k. And what 1 over k is your DC gain. So k has units of newtons per meter, and so the inverse 1 over k is meters per newton. In other words, if you input just a constant force of, say, 1 newton, you're going to get k times that 1 newton meters out of the system. So if r is like, I don't know, 3 newtons, and you have a spring constant of 1, then you're going to get 3 meters out of the system. It's going to oscillate about 3 meters and settle on 3 meters if it's underdamped. If it's overdamped, it'll just slowly approach 3 meters and stop. Okay. Let's move on. Oh, well, first I'll talk about units of k. So in our vibrations lab, we did a torsional disk. And if you remember that one, we did a step input. And so we applied, I don't know, some torque as an input. Let's call it 5 Newton meters for torque. And it looks like this. This is what a step input looks like, the blue line. And our response was like this. Maybe it oscillated about 10 radians and it settled on 10 radians. So our output's in radians. That's what we're interested in. And our input is torque. That's what we inputted to the system. And so our DC gain here is 2, right? 2 radians per Newton meter. That is our DC gain. Okay, and it's also 1 over the spring constant. So let's move on. You could simulate a bunch of different step inputs in MATLAB. So how do we do this? Well, we'll make a generic second order system. So our numerator is 1, and which means that our k is 1, and it means that our natural frequency squared is 1. So very simple system. We also know that natural frequency squared is 1 because we have a 1 here, right? That's the wn squared place. So all we're changing is zeta. 2 zeta wns, we said wn was 1. All we're changing is zeta, 2 times zeta. And so for different values of zeta, we get our different responses. As we expect from vibrations, the lower values of zeta oscillate more about the equilibrium value. And the higher values of zeta become more and more damped until you get critically damped. That's this line here. It's the fastest response to settle on that equilibrium value, and then we go to 2. That's this line here. It's overdamped. It takes a long time for it to reach that value. Okay, so what about an impulse? Well, an impulse is like a step, but it only occurs for an instant, right? It's just, there's a torque, there's a force, and then there's not. So we do different values of zeta. We do 4 different values for some, generic transfer function. We use the impulse function, right? Whereas above we use the step function to simulate a step response. We use the impulse function here with our system and our time, and then we get these responses. So as we expect, the underdamped systems oscillate more. The overdamped systems don't really oscillate at all. They go up because of the initial impulse, and they settle back down to 0 without oscillating again. So let's do some examples. So let's say we have a robot that follows around someone, and its control is g of c, and that's k1 plus k2 over s. But then the robot itself actually has some dynamics. So it's got a mass, it moves around. This is a first order system, right, where tau is the time constant. So that means that if you say go here, then it's going to exponentially kind of approach it. That's what a first order system looks like. It kind of looks like, and you're kind of getting there, and you're pretty much there. There's no oscillating. But what if we input, say, a triangular wave? If we input a step, it's gonna, okay, slowly get there. If we say, okay, go here, and then here, and then here, which is what we do here, we input a triangular wave, which is pretty much a bunch of ramps put together. So there's a ramp up, there's a ramp down, there's a ramp up, and we can simulate the response of our system. So you can see that our system has some dynamics, right? It doesn't just match it exactly. It's like, okay, we're going up. I'm going to go up now, and then, oh, we're going down, we're going down. That has to do with this time constant here. And I'll do this example more in depth for you guys. So we can actually see some performance characteristics straight from the graph. And how we do this is just by looking at the graph, right-clicking, and we can see things like peak response, settling time, rise time, and our steady state value. Pretty self-explanatory. Okay, this other example I'll do in a separate video, but I'll briefly talk about it. So let's say we have a system here, and we have some disturbance being inputted before our load. So our load is like what we're moving around. In this case, it's a disk read system. So we're moving about that read pen or laser or whatever it is. So this is the pen or laser dynamics, right? This says how it behaves. Looks like it is not a first order system, something else. And this is what goes into it. So we apply, some input. We say we want to go here, or we want to move it somewhere. It amplifies our input. The motor has some constants, so that's also some amplification. And then we have some disturbance. I don't know, maybe you're jostling your computer around. We don't know what it is. We'll just call it T of D, and that goes into your read laser. And then it's a feedback system, so that's used to, as you know, make the system more accurate, so it will be much better at getting to less error in the steady state. Okay, so we want to find a gain, Ka. So this is the design problem. We want to pick a gain here such that we meet these requirements. We want our peak overshoot, our percent overshoot, to be less than 5, right? That's how the system moves past its initial, or its steady state value, right? It overshoots. So we want that percentage to be less than 5%. Our settling time, that's the time it takes to get within, say, I don't know, 5% of the final value. We want that to be pretty quick, less than 250 milliseconds. And this last one is something new. We want our maximum value of response to a unit step disturbance to be less than 5 times 10 to the negative 3. Okay, so here we go. The first things we want to do is find y of s over r of s and y of s over t d of s. So this is saying, let's ignore, right, this part, y of s over r of s. let's ignore TD, let's say it's 0 and just solve the system. Right, so we just collapse this in series, and then these are all in series, and then one feedback loop, right, if we ignore TD. And the second one is if we ignore R of S. We say there's no input, right, R of S is 0. Let's solve for Y of S over TD. And this will be used to verify that we're meeting our system requirements. And again, I'll go over this in a much more detailed video for this specific problem. And here's the code for plotting. And basically you experiment around with different values of Ka, and you see, oh, well, this this overshoots that much. Let's increase or decrease Ka and see how that affects it until we get system performance values that meet our requirements here. Okay, so with that, I'll leave you to do the lab tasks. And yeah, look for a video on the disk drive read system and on the robot that follows you around. Where's that? Right here. Okay. See you guys on Wednesday.